Welcome to this e-learning video where I will give a short introduction to the S6 model. Here, the 6 S's stand for single species, size structured, and steady state. I will present a short overview of the model structure, the required input, and then also show you how to get started with the R package. Lastly, I will also briefly introduce an adaptation of the model to estimate biological reference points according to maximum sustainable yield for unexploited mesopelagic species. The S6 fish stock assessment model is developed to use information of individual size or body weight from catches to assess the level of exploitation of data limited stocks. So the model is based on size-based theory, where a stock can be defined by its asymptotic size, W infinity, and a set of Beverton and Holt life history invariants. Now, combining these few parameters with the size distribution from the catches then allows the model to estimate the status of the stock. So the stock status is the ratio between the fishing mortality and the reference point FMSY. And then the model essentially classifies stocks as over or underfished. So overfished when the ratio is above 1, underfished if the ratio is below 1. The size-based theory is described in detail in this book shown here, while the model itself, the stock assessment model, is described in detail in these two scientific articles. All of those you can also find in the list of references at the end of this presentation, and hopefully also in the attachments to this video. The S6 model is size structured, and particularly in data limited situations, size-based methods are highly valuable. And that is because information about the size distributions of catches is relatively easy and cost effective to collect. And also often length or weight data is already routinely collected during ecosystem surveys. So therefore, this type of data is more readily available in data limited situations compared to age data, while also providing equivalent representations of demography. Additionally, most vital rates of individuals are also strongly related to body size. For example, food availability or trophic level, vulnerability to predation, and also selectivity of fisheries are strongly tied to the size of a fish. However, also, as with many stock assessment methods, there are limitations and biases related to length and size-based assessment methods that one definitely should be aware of. For example, they can be sensitive to the accuracy of the life history information provided, to recruitment variability, and also to non-representative sampling, of course, caused by, for example, biased sampling schemes, insufficient sampling size, or insufficient sampling frequency. As mentioned before, the S6 model is structured around body size. So for an individual size W, growth and reproduction are defined by a bioenergetic budget where the available energy can be allocated to activity, to reproduction, or to somatic growth. The total available energy follows an allometric relationship with a growth constant A and an allometric exponent N. Energy can be allocated to activity described by the constant epsilon A, and that includes, for example, energy necessary for movement or for food assimilation. Reproduction is only done by mature individuals, where maturation is described by a sigmoid maturity ogive around the 50% maturity size at M. And then the remaining energy after using it for activity or reproduction is invested in somatic growth. The mortality, on the other hand, of an individual is size dependent, and it is the sum of the mortality due to natural causes and the mortality due to fishing. Natural mortality involves all mortality that is not induced by a fishery, for example, mortality due to predation, disease, parasites, or senescence. And it is here described as, again, an allometric relationship with an exponent of, this time, n minus 1. And then also the physiological mortality A. This parameter is highly influential in describing a stock, and it is the equivalent of the M over K ratio, but then adapted to size-based mortality. On the other hand, fishing mortality only occurs for individuals large enough to be caught by the net. And this again is described by a sigmoid selectivity curve with a 50% retainment weight W50. And such a sigmoid curve follows the behavior, particularly of active fishing gears, such as trolls. The individual level dynamics are then scaled to the population level by using the McKendrick von Forster mass conservation equation. Now, this equation includes the growth and the mortality rates shown in previous slides, and its steady state solution gives a size spectrum, as shown here, with the dotted lines indicating the size at 50% selected by the fishery and 50% maturation. So generally, the abundance in a size group is a balance between how many individuals grow into the size group, how many grow out of the size group, and how many individuals die. The boundary condition of the equation is formed by the recruitment R into the population, and that is the individual influx into the population, or the number of individuals that enter into the smallest size class with body size WR. The Beverton and Holt stock recruitment relationship then connects the spawning stock biomass with the recruitment. The reference point, FMSY, is then calculated by maximizing the yield with respect to fishing mortality F. Yield can be found by integrating over the size distribution multiplied by a size selectivity curve of the fishing operation. And generally, the life history parameter determining recruitment and therefore strongly affecting FMSY is the recruitment efficiency epsilon R. The model requires size distribution data from catches with a minimum data requirement of length or weight data collected in every month throughout 1 year. It also requires a set of life history parameters that remain constant during the estimation. So these life history parameters are considered to vary between species and can be found from cross-species analysis. Though some of the parameters can also be approximated when other population dynamic parameters, such as the von Bertalanffy constant K or the natural mortality M, are known. The model then estimates the fishing mortality F, the 50% retainment size relative to W infinity, and W infinity or the asymptotic weight. If data for multiple years is available, a single W infinity is estimated across all available years, while the other parameters are estimated independently for each year. The parameter estimation is done using maximum likelihood. As part of the MESO project, we have adapted the S6 model to also be able to estimate reference levels for unexploited stocks. Because with a continuously increasing global human population and the corresponding increase in the demand for marine products, there is also an increasing interest in the exploration of new marine resources. On top of that, climate change affecting the distribution of marine fish populations and the species composition in catches might also require the evaluation of exploitation of potential new opportunities. For such new and developing fisheries, access control is necessary from an early point in time. In initial stages, it is necessary to put a conservative cap, both on the fishing mortality rate and the fishing capacity, but it's also necessary to establish preliminary biological reference points according to the stock-specific maximum sustainable yield, ideally already in the planning stage. And this is what we have done in this work for 2 mesopelagic species. Unexploited fish and shellfish stocks are highly data limited. Since there is no fishery, there is very limited information available from previous catches or landings. And it can also be expected that there is no sufficient time series of age data available, since the collection of such data is time-consuming and costly. However, as also mentioned at the beginning of this presentation, data of fish length and fish weights are often routinely collected during ecosystem monitoring surveys, or alternatively, could relatively easily be collected over the course of a year if there is an interest in the sustainable exploitation of new resources. Size-based methods are highly suitable in unexploited conditions. Now, for unexploited stocks, we can further assume that the fishing mortality F is very close to zero, and that also the total stock biomass approximately equals the virgin stock biomass. Therefore, in unexploited conditions, it is possible to directly estimate the fisheries management reference points FMSY and BMSY. They, however, strongly depend on assumed values for the gear selectivity of the fishery and on the virgin biomass assumption. Additionally, in unexploited conditions, the physiological mortality A can be estimated, which is the most influential parameter in the assessment model and difficult to measure. The physiological mortality essentially connects the natural mortality to the available energy and therefore growth. And in this manner, the observation that small and fast-growing species have a higher natural mortality compared to large and slow-growing species is connected. And another characteristic of unexploited species is the general uncertainty, particularly associated with the population dynamics. This is also the case for the two mesopelagic species under investigation. Maurolicus muelleri and Benthosema glaciale are of interest for potential exploitation due to their potentially high fat content and also potentially high abundance in the Northeast Atlantic Ocean. So the orange points here indicate sampling locations for each of the species. And for Maurolicus, we analyzed one size distribution from 2020, covering 3 months, while for Benthosema, the data availability covered multiple years. For each of the species, we estimated the physiological mortality A and the biological reference levels FMSY and BMSY, taking into account the uncertainty in the life history input parameters. This we did by randomly sampling from normal parameter distributions with species-specific means and standard deviations of the growth constant A, the size at 50% maturity eta M, the activity coefficient epsilon A, and the recruitment efficiency epsilon R. And since there is still considerable uncertainty in the species-specific biomass estimates in the Northeast Atlantic Ocean, we evaluated BMSY according to different scenarios of absolute biomass, which were for the two species based on literature. Using this approach, it is possible to generate distributions of all estimated parameters, as can be seen on this figure here for Maurolicus muelleri. Here, for example, panel A shows the parameter distribution of the estimated physiological mortality. Panel B shows the distribution of FMSY. And panel C in the bottom shows the distribution of BMSY for the different scenarios of low, intermediate, and high total biomass. And the figure here on the right shows the model fit to the size distribution data. This was just an example of the type of results you can become using the S6 model applied in highly uncertain and unexploited conditions. Overall, the S6 model is developed in R and the package is open source, which you can find through the GitHub link here. Code for the installation of the package is shown here on the slide, but can also be found on GitHub. And there you can also find vignettes or manuals with examples of assessments of North Sea and Eastern Baltic cod stocks using the S6 model. More information on the model and on the size-based theory upon which the model is based can be found through the references here.